Today in section 5.4, we're going to talk about inner products. So we already called the scalar product in Rn the inner product as well, but here what we mean by inner product is a much more general thing. We're going to take an arbitrary vector space V, so this doesn't have to be Rn, and we're going to define an inner product to be anything that combines two vectors, so two vectors x and y. Essentially, we'll multiply them together to get a real number, and we denote it as x comma y inside angle brackets. And this will be any possible way of doing that that satisfies these three conditions. The inner product of a vector with itself has to be a non-negative number, and that inner product with itself will only equal 0 if the vector is 0 to begin with. We'll also say that the order doesn't matter, so the inner product of x and y is equal to the inner product of y and x. And we can also take a linear combination in the first slot and pull it apart. So the inner product of alpha x plus beta y with z is just equal to alpha times the inner product of x and z plus beta times the inner product of y and z. Now you might think, why can't we do that with the second slot? We actually can, because we're able to swap the order. If we wanted to take the inner product of, say, x with alpha y plus beta z, we can just swap that to the front using our second property. There should be an angle bracket. We can then split it up using property 3. And then we can swamp the y in x and the z in x so that we get exactly what we would expect to be there. We just don't have to state that as a separate property because it is implied by the other ones. So we get that one kind of for free. We don't have to prove it if we're going to prove that something is an inner product on a vector space. If a vector space has an inner product, and we know which inner product we're talking about, then we'll call that vector space an inner product space. And a lot of vector spaces that we work with already are inner product spaces, with particular inner products anyways. Pretty much every vector space can have some sort of inner product put onto it, but there are different ways of doing so. So let's look at a few examples. So our first example will just be Rn. Rn specifically with the inner product x comma y, the inner product of x and y will just be x transpose y. Just our normal way of our normal scalar product in Rn. That is an inner product. It satisfies these conditions. We're good. You can, in some ways, call it the standard inner product in Rn. But we could also find a different inner product in Rn. So here, we're going to work with Rn, and we're going to introduce a collection of w's. And we're going to define our inner product of x and y. Here I'm thinking of x and y as bold vectors, bold column vectors, where x is x1 through xn, y is y1 through yn. I'm not going to write that out, but our formula here would be something like w1 x1 y1 plus w2 x2 y2 all the way through wn xn yn. So here, instead of just doing like we did in our standard scalar product, where we took x1 y1 plus x2 y2 and so on, we have these w's in front of each of these. These are called weights. This is called a weighted inner product. And it's basically a way to say, well, maybe I want my first component to be a little bit more significant when I take that inner product. I could make the w1 bigger than all the other w's. something like that. And this is also an inner product on Rn. That's different from the standard inner product, the standard scalar product that we've been talking about. Another pretty common one, C of AB. So remember, this is continuous functions on the closed interval a to b, specifically real valued functions. So if we take the inner product of two functions f and g, a nice way of doing that is to take the integral of the product of those two functions on the interval a to b. This will actually satisfy all the conditions that we want for an inner product. We can actually do a similar trick as we did in 2. So have, again, the C of AB. Here we'll have some sort of weight, but this time it's going to be a weight function. This will be a function defined on the entire interval from a to b. And then we define our inner product now as still being the integral from a to b of the product, but we stick our weight function in there as well. Now, there's a couple conditions here. We need to make sure that w isn't 0 for a lot of the interval and stuff like that. Just like up here with these, we need to make sure these w's aren't 0. Stuff like that. So not every selection of w's or w function can actually make an inner product, but as long as things don't get to 0 to kind of mess with this first property, we're all good. Now, there's a few other ways. The book defines an inner product for the polynomials Pn. It's a little bit more complicated, so maybe we won't go over that, and we're not going to be using it for any of our examples. But just be aware that there's a lot of different ways of getting examples of inner products. But it's just a way of combining two vectors, whether those are vectors in Rn or functions in a CAB. Just combine those to get a real number. Oops. Another thing that we're going to be looking at is called a norm. Norm is kind of a generalization of our idea of magnitude or length of a vector. And we're going to say that a norm is any function that takes a vector in a vector space. So we're working with an arbitrary vector space. Takes a vector in that vector space to a real number. It just takes that vector and gives you its length. Here we're just going to call it the norm. Now, it does also have to satisfy 3 conditions. First of all, the norm of any vector is always a non-negative number, and it's only equal to 0 if that vector was the 0 vector. The norm of a scalar times that vector, if we multiply a vector by a number, that multiplies the norm of that vector by not that number specifically, because we had to have it be a non-negative number. The norm has to be non-negative, but it's going to multiply it by the absolute value of that scalar. And finally, we have that the norm of a sum of two vectors is not equal to, but is less than or equal to the sum of the norms of those vectors. This is referred to as the triangle inequality. And the idea here is if we take, so working with vectors in Rn, if we have a vector v and a vector w, remember the vector v plus w, make that actually go to here. V plus w goes from the start of v to the end of w if they're stacked on end to end like that. And what the triangle inequality is saying is that the distance from just going directly from here to here is shorter than the distance that if we kind of made this more of a detour following v and then w. So In that sense, it makes a lot of sense, but this is going to have to be true even if this norm is not really even a property of length, even if we're working in a maybe our vectors are functions, something like that. And I'm going to give you a lot of examples of norms that are based off of what we just talked about in the last page. But I do want to mention some other norms that actually come from different places. So let's look at examples. Specifically, we're just going to look at examples in, not examples if, examples in Rn for now. First example, so here x is just going to be the vector x1 through xn, and I'm going to put a 2 here. This is going to be the norm where we take x1 squared plus x2 squared all the way through xn squared. And then we take the square root of that sum. This is frequently what we'll call the 2 norm. And it's kind of familiar. This is what we've been using already. It's the norm that we talked about before as the magnitude or length of a vector in Rn. It's just not the only norm on Rn. Another norm, or actually, this is more. It's this the 2 norm is a special case of a more general family of norms called the p norms. So for any p, well, not any p, we need p to be at least 1, and then, well, it can go off to infinity. Any number bigger than or equal to 1, this can work for. We'll take x1, we have to take the absolute value just in case we're not dealing with a power that's an even integer. But here we not only do we not necessarily have even numbers, but we also might not even have integers. Technically here we could take 3 halves, and then we'd be trying to take square roots, and we want to make sure that we don't put any square roots into our into our pth power. Or, well, sorry. What I'm trying to say is we want to make sure we're not putting any negative numbers into our pth power, because if we're dealing with square roots, that's not going to really be very helpful. We're going to be getting complex numbers there. So we'll take x1, we'll make it positive, and we'll take it to the pth power. We'll do the same thing for x2, and we'll add those all up till we get to xn to the pth power. And then, similar to how we had to take the square root up here, we are going to take the pth root. So technically, the 1 over p power. This is an example of a norm, at least as long as the p is at least 1. If it's less than 1, we can actually get some of these properties not working anymore. So this is a nice example of a norm, or a family of norms. Specifically, if we look at the 1 norm, here all the p's are 1s, 1 over 1 is 1, so really all we're doing is taking the sum of the absolute values of all the components of x. We're just adding them all up. This is sometimes actually called the Taxicab Norm. Kind of the idea here is that if we have a city where our streets are all perpendicular to each other, a nicely laid out city, then we can measure distances, lengths of lengths of vectors. So if we have a vector, say, going from this point to this point, we're measuring the distance along here and the distance along here, and we're adding those two distances together in order to get the length of this vector. Instead of going straight across, we're taking these two lengths and adding them together. And Why it's called a taxicab norm is because, well, that's the distance a taxicab would have to drive to get from this intersection to that intersection. So it's a okay way to measure distances in certain situations. And that's really what we're doing with norms. We're trying to measure distances in different ways. Our last norm that we're going to look at on Rn, or the last norm that we're going to talk about for the moment, is called the infinity norm. We'll put norm with a little infinity down here. And this is equal to the maximum of all of the x, or the absolute values of all the x's. So here, I is going from 1 to n. So we're saying, what is the biggest one of the absolute values of x1, x2, all the way through xn? Which one of those is biggest? That's what we're going to call the infinity norm. And it does satisfy those conditions. So, very famous norms. Technically, we could get into some norms of functions that are similar to these. There's actually versions of the p norms and infinity norms for functions. I don't want to get too much into that, but this is a very broad concept that's actually very used in a lot of cases. So if this section is all about inner products, why are we talking about norms so much? Well, it turns out any inner product space, is a norm space. Every inner product gives a norm, using the same definition that we used for the magnitude of vectors when we were dealing with the scalar product. We take the inner product of a vector with itself, and we take the square root of that. And that will give us a norm on our vector space. And let's actually go ahead and prove this. The first two parts are relatively easy. The third one will be a little bit trickier, but we'll get to that. Actually, even before we start proving the first property, we need to know that this even makes any sense. Remember, one of the properties of being an inner product space, or of this angle bracket being an inner product for a vector space, is that the inner product of a vector with itself is always a non-negative number. That means that we can take the square root of it. We're not going to be getting any complex numbers here. And that leads right into talking about about the actual properties of being a norm. We want to be talking about the positive root, or non-negative root, in the case where we actually get a 0 here. So the norm, the square root, is going to have to be a non-negative number. That's the first part of property 1. The other part of property 1 is what happens when the norm equals 0. We want to know that this only happens when v equals 0, and that it does happen when v equals 0. Well, if v equals 0, we already know that the inner product of v with itself is going to equal 0. So this norm is definitely going to be 0. But if the norm of v is 0, the norm of v being the square root of the inner product of v with itself, well, that just means that the inner product of v with v equals 0. And so, well, that's one of our properties from inner product, says that if the inner product of a vector with itself is 0, that vector is a 0 vector. So, kind of this is just the first property of a norm being the first property of something being a norm is very much related to the equivalent property for something being an inner product. Property 2. Here, we want to look at what is the norm of a scalar times a vector. And we just want to somehow be able to pull out that scalar. Well, we'll go ahead and use our definition here. This is the square root of the inner product of alpha v. So the inner product of alpha v with itself. Remember, when we have a linear combination in the first slot, we can go ahead and pull out those coefficients and split over the sum. We don't have a sum here, but we can pull out that alpha. But remember, we also talked about being able to do the same thing in the second slot. So we can pull this alpha out too. So I'm going to have an alpha squared out here and just the inner product of v with v. Okay, we can split this up. What is the square root of alpha squared? Note it is not alpha unless alpha is positive, or non-negative. I guess it works for alpha equals 0 as well. But if alpha is negative, we get negative alpha. Or in other words, the square root of alpha squared is the absolute value of alpha. And then we have the square root of the inner product of v with v, but that's exactly what we were calling the norm of v. So this is exactly what we wanted. We can pull that alpha out, and we get an absolute value of alpha on the outside. Third property. Well, this is the triangle inequality, and it's going to be a little trickier. In fact, it's going to be so trickier, we're going to actually go and prove another theorem first and come back to this. So let's prove this theorem first. We're going to make use of this one pretty well, and it's actually a pretty important inequality itself, called the Cauchy-Schwarz inequality. If two vectors u and v are in the inner product space V, then the inner product of u and v, or at least the absolute value of that, is less than or equal to the product of the norms of u and v. Now, we're just kind of assuming here that we already know that those are norms. We don't necessarily need to know that to prove this. We can just think of the norm of u just being a shorthand for the square root of the inner product of u with u. We're not going to use any of the properties of norms to prove this. So it's not going to be a circular argument. So let's actually prove this. I'm going to prove it in a little bit different way than the book actually did. We are going to look at the inner product of a linear combination of u and v, so alpha u plus beta v, with itself. Now, why did we do that? Well, because we can use the first property of inner product. This is an inner product of a vector with itself. It is a non-negative number. But we are allowed to split it up. We can split this first part up. So we have alpha of u inner product with this, plus beta times v inner product with this, and then we can do the same thing, split up this part. Really what that boils down to is we can FOIL this out. We can take our first, pull out the alpha, so we have an alpha squared times the inner product of u with u. We can take our outers, so alpha u and beta v, we can pull out the alpha and beta. Then we have our inner ones, beta v and alpha u. We can again pull out the alpha and beta. And finally, we have our beta v and beta v. Pull out the beta squared. Okay, now what can we do? Well, first things first. The inner product of u with u, that's actually the norm of u squared. Remember, the norm is the square root of that, so we're basically moving the square root to a square on this side. We'll also do the same thing over here, but I'll leave that for a moment. What are these two things? Well, we have the same alpha and beta in front of them. But uv, the inner product of u and v, and the inner product of v and u, those are the same thing. That was one of our properties. So I'm just going to go ahead and combine these into one term, where I have two copies of it being combined. And then again, doing exactly the same thing we did with the alpha and u, we do with the beta and v. Alright, now what do we do? Well, I didn't pick alpha and beta at first because I'm going to use this result here, the fact that this thing that we have here is bigger than or equal to 0, but I'm going to put in particular alpha and beta that actually help me out. My first choice, I'm going to pick alpha to specifically be the norm of v. And I'm going to pick beta not to be the norm of u, but to be the negative of the norm of u. What does that mean? That means what I'm going to have here is I'm going to have the norm of u squared times, well, this is going to be the norm of v squared, plus, well, 2 times the norm of u, norm of v. Well, actually not plus in this case, actually. There you go. Because, well, when we put in the beta, we had to put in a minus sign. And then we're going to have this inner product. And then here, the beta squared, well, that's going to get rid of the minus, so we actually have a plus. And we have a norm of u squared, norm of v squared. And this thing has to be non-negative. Or in other words, if we divide everything by the norm of u times norm of v, we have norm of u, norm of v. I'll put a little dot here to kind of break up that 4 lines. Should probably do that here as well. Well, this norm of u, norm of v, those are going to go away. Now, I'm kind of assuming here that neither u or v is 0. If either of those is 0, then we can't actually divide by the norm of u or v. But in that case, both sides of this inequality are going to be 0 anyways. So I'm kind of excluding that case. Okay, so we've got this thing now. And what does this mean? Well, if I move the inner product of u and v to this side, and I combine the norm of u times the norm of v, that happens twice, and then go ahead and divide out that 2 because it wasn't really too important. We have the 2 here, and we'll have a 2 on this side. We have that the norm of u times the norm of v is bigger than or equal to the inner product of u and v. Now that's not exactly what we have up here. This is saying that the absolute value of the inner product of u and v has to be less than norm of u, norm of v. And if the inner product were a negative number, well, this would definitely always be true anyways. If in that case, the absolute value of the inner product of u and v might not be less than or equal to, at least from this part of the proof. So we're going to have to do this again. I'm going to kind of split this up. We're going to have a second choice. This time, actually I'm going to still pick alpha to be the norm of v, but this time I'm going to go ahead and pick the norm of u. So a lot of it's the same. We're still going to have the product of 2 norms here. This time, instead of a minus, we have a plus. And remember, the minus sign went away in this case anyways. So really, the only thing that changed was that minus sign is a plus sign now. We're going to go ahead and divide out by norm of u, norm of v like we did before. And it's going to look exactly like the second line here, but with a plus sign instead. I'm not going to write it out again. I'm going to skip to actually solving. Because now what happens when we bring the inner product of u and v to the other side is we'll have a negative. Basically, this is going to turn into norm of u times norm of v is bigger than or equal to the negative of the inner product of u and v. And so, no matter if the inner product of u and v is positive, well, then we can just use this first one, and that's what this inequality is saying. If the inner product of u and v is negative, then the negative of that inner product is then the absolute value, and so we have this inequality again in that case. So either way, no matter whether or not the inner product is positive or negative, we're still good. All right. So what can we? How does that help us in proving the triangle inequality? Well, let's actually just kind of start with the norm of v plus w. To kind of not have to deal with square roots, we're going to go ahead and square that, and then we'll go ahead and unpack that and see what we can get. So remember, the norm of v plus w, by our definition, it has the inner product of v and v plus w with itself. We don't have to take the square root because the square is here. We can go ahead and expand that out exactly the same way we did in the last one. Except now we don't have to deal with that with alphas and betas. And then what do we have? Well, this is norm of v squared. Again, these are the same thing, so we'll go ahead and put a 2. And then we have norm of w squared. And if we didn't have the Cauchy-Schwarz inequality, this is where we'd have to stop. But we know that this is less than or equal to the norm of v squared plus 2 times the norm of v times the norm of w. I mean, technically here in the inequality we had that the absolute value was less than or equal to this, but the absolute value is either plus or minus this, whichever one is bigger. So this one is definitely going to be less than or equal to that. And then what is this? Well, just using some algebra, we have something squared plus 2 times that something times another thing plus that other thing squared. That's just equal to the square of the sum of those two things. If you don't remember this one, try replacing the norm of v with a and norm of w with b, and this is just the square of a plus b is equal to a squared plus 2ab plus b squared. And now what do we have? Well, we can take the square root. This thing here, once we take the square root, is less than or equal to norm of v plus norm of w. And that's what we wanted. So that's our triangle inequality, and it shows that this definition does give us a norm. So any inner product space can become a norm space. Now it is worth noting that doesn't go the other way. Not every norm has this associated inner product. In fact, if we go back and look at the norms that we talked about on Rn, the only one of these that can come from an inner product is the 2 norm. All the other ones cannot. I mean, it's not that we just haven't found a norm. We know that they cannot come from an inner product. So that's kind of why we study the 2 norm rather than these other ones for the most part. I mean, we use these other ones, but the 2 norm definitely stands out as being the most important because it is involved within inner product space. All right. Oops. Now, one little last thing. This is a bunch of definitions, but they're all definitions we've seen before. We're just taking the same ideas that we had for our scalar product, and we're going to apply them in the same way for our inner products. Inner products and norms. So if we're talking about norm as being a length of a vector, we can talk about the distance between two vectors as being just the norm of their difference. Since we know the Cauchy-Schwarz inequality, we're basically saying that the inner product of u and v is between well, it's less than the product of the norms, but it's also bigger than the negative of the product of the norms. Which means that if we divide by the norm of u and the norm of v, the inner product over the product of the norms is going to be a number that's always going to be between -1 and 1. And so we can actually define angle even in situations where angle doesn't make any sense, like if we're talking about our vectors being functions, we can talk about the angle between two functions by basically saying that this inner product over the product of the norms is the cosine of that angle. There's a unique angle between 0 and pi that will make that true. And that's what we will call the angle, even if that, in a sense, doesn't make any sense to us. This is the sense that we mean. We can talk about two vectors being orthogonal if their inner product is 0. So just the same way that we were talking about it before. And if we use this concept of angle that we have up here, what does that mean? Well, when is the cosine of theta equal to 0? Exactly when the angle is pi over 2 or 90 degrees. So in a sense, we can say that orthogonal still means perpendicular as long as we mean 90 degrees. But we just use the term orthogonal. We still have the Pythagorean law that if we have two orthogonal vectors in an inner product space, we can actually split up the square of the norm or the sum into the sum of the norms. Sum of the squares of the norms, I should say. And the proof of that follows almost word for word the same way that it did for the scalar product. So I'm not going to bother proving that one again. Finally, we can talk about scalar and vector projections. The vector projection being the more important one of these two. And we're just going to define these to be exactly the same thing that we're defining them to be the same formulas that we derived before. Before, we actually started with a geometrical idea and we derived formulas that fit that geometrical idea. Here, we're just going to say these are our definitions. The projection of u onto v is this scalar multiple of v, as long as v is not 0, not the 0 vector. But it turns out it'll fit what we mean by projection, that the projection will satisfy these two properties. That if we take the projection vector p, and the vector u minus p, those are orthogonal to each other. So if we kind of imagine here we have our, let's say this is our vector v, we have our vector u, make that more like a u. We'll have some vector p pointing in the same direction as v. That's related to our u. It's the projection. We just think of this as kind of moving down to here, kind of the shadow on v. And then u minus p would be the vector here. And those are supposed to be at right angles. They're supposed to be orthogonal. And this is saying that if we use this definition, those are going to be orthogonal, even if they don't necessarily fit this geometrical idea, because, well, we're not actually working with arrows. We're working with, I don't know, functions or something more abstract than that. And then u equals p if and only if u is a scalar multiple of v. That basically means that the only way that u and p can be the same thing is if u is already on v to begin with, in which case we don't really need to be doing anything to project onto v. But it all fits the same kind of definitions, and we don't really need to do any new work. We're just repeating the same old work. The important things are the definitions of inner product and norm being based off of these different properties of these functions, rather than being something we derive from some formula that we started with. Okay, so That video got a little bit long-winded, but I'm kind of sorry for that. But we'll go ahead and work out a few problems in the next video, and then we'll move on from there. So see you in that one.